Hello and welcome to helpyourmath.com. In this video, we're going to look at sketching transformations of absolute value functions. Before we get to the transformations, let's review what an absolute value function is. The graph looks like this, and the parent function is f of x is equal to the absolute value of x. So it's symmetric about a vertical line containing a point called the vertex. So I like to really focus on the vertex here. The vertex is really nice on the parent function, it's 0, 0. And then based on the given transformations, it'll move around the graph. Now, I like the vertex because it does give me symmetry around it. So I know if I go 1 unit to the right of the vertex, I'm going to have the same output as if I go 1 unit to the left of the vertex, right? So those both give me an output of +1. And then the same thing would happen if I go 2 to the right. That will be the same as going 2 to the left. So I focus on the vertex and where the vertex appears in the transformed graph. When we graph absolute value functions or functions in general, we look for 3 types of transformations. We look for vertical or horizontal shifts. Those will be given in the equations of our transformed functions. So a vertical shift would be of the form something happening to the function and then plus or minus k. And a horizontal shift will occur within the function and it will be x minus h will move the graph left or right from that 0, 0 vertex. We could also find a reflection about the x-axis. We don't have to worry about a reflection about the y-axis because if you reflected it about the y-axis, you would actually end up with the same graph anyway. And we'll also look for non-rigid transformations. Those would be vertical stretches or shrinks. And I'm going to show the first one while also using a table of values, but I do want to try to break away from using the table of values and just relying on our knowledge of absolute value functions. So we know we're dealing with an absolute value function when we see that V-shape graph. And so we want to use that and all of these other things that we know about transformations of functions to be able to graph it without the table of values. But I will show how to use a table of values. There's nothing wrong with using a table of values. It's just very time consuming. Okay, so here we are. We're going to name the parent function f of x for the given function. We're going to describe the sequence of transformations to get from that parent function to the function that we're given g, and then we're going to sketch the graph of g. Okay, so what was the parent function here? Well, the parent function would have been f of x is equal to the absolute value of x, because that's what we're dealing with in this video. So first part is done. Now, what happened from f of x that's going to get us to g of x? Well, it looks like we moved the graph up 3 units. There was a vertical transformation where our graph is going to be up 3 units. So what this means is that, remember that parent function that started at 0, 0? Our vertex now on this graph is going to be up 3 units from 0, 0, which would be at 0, 3. That vertical shift is the only transformation. That's the only thing that's going on here. That's the only difference between our parent function and this function g. Okay, so like I said, what we can do is make a table of values. When you make this table of values, you definitely want to be able to identify the vertex as you go through this because you want to pick points around the vertex. So I'm going to put 0, 3 in the middle. And again, if I wasn't sure that it really was 0, 3, I could always plug in 0 to the given function and make sure that I get 3 on the output. And then I also want to input, we'll go 1 to the left of 0, which is -1, and 1 to the right of 0, which is 1. 2 to the left of 0 is -2. 2 to the right of 0 is +2. And what's going to happen is -1 and 1 should give us the same output, so I only need to calculate one of them because everything's symmetric about the vertex. I'll show you that they end up being the same, and then I won't do that for the 2 and -2. So if I plug in g of -1, I take the absolute value of -1 and then add 3 to it. Well, the absolute value of -1 is 1, and 1 plus 3 is equal to 4. So here our output is 4. I'm predicting that when I plug in 1, I will also have an output of 4. G of 1 is equal to the absolute value of 1 plus 3. The absolute value of 1 is 1, and 1 plus 3 is 4. Okay, so when we look at 2 and -2, choose one of them. It doesn't matter which one. Since I have more room up here, I'll choose I can work over here. I'll choose -2. So G of -2 will be the absolute value of -2 plus 3. The absolute value of -2 is 2, and 2 plus 3 is 5. So we have -2, 5, and we know that because it's symmetric, it will also be 2, 5. Now we're ready to graph this. We're going to start at 0, 3, our vertex. And because there's no non-rigid transformations, there was no stretch and no shrink, we also know that to find other points, we would go over 1 and up 1. to the left 1, up 1. Over 1, up 1, to the left 1, up 1. And you can see these are the points 1, 4, which we have right here, negative 1, 4 we have right here. This is 2, 5, and negative 2, 5. And eek, you want to use a straight edge. The good news is I graphed it so you don't have to look at my terrible attempt at it. That's what our graph of g of x would look like for this particular example. So this one I did the table of values. Feel free to use the table of values for the next examples, but I'm going to try to not use them. Okay, here we have g of x is equal to the absolute value of x plus 1 inside the absolute value minus 4. So what's the parent function for this? Well, what do we see here? We see an absolute value. So I know that our parent function f of x is the absolute value of x. What happened from our parent function? How is this moving in the coordinate plane? Well, I see there's something going on within the absolute value, which means that we have a horizontal shift. So this is a horizontal shift. Remember, when it's inside the absolute value, it's always the opposite of what we think. So the horizontal shift is going to be, it says plus 1, but really what we're looking for is x minus h. This would be x minus negative 1. So we're actually moving to the left 1 unit. So we're moving to the left 1 unit. Left 1. And then we also have this out here outside of the absolute value. That indicates that we have a vertical shift. It's a minus 4. That means it's going to go down 4. I like to use this information, the horizontal and vertical shift, to tell me where the vertex is of this graph. And the vertex of this graph will be left of 0, 1 unit, that would be negative 1, down 4 would be minus 4. So this graph is going left 1, down 4 down here. And then there's no negative, so there's no reflection about anything. And there's no coefficient. Well, the coefficient is 1. So that indicates there's no non-rigid transformations, which means this absolute value function from here, we can find more points by starting at our vertex, going up 1, over 1, up 1, to the right 1, over 1, to the left 1, up 1, to the right 2, up 2, to the left 2, up 2. And if you're ever really concerned about this, please plug in the values, right? So what is surrounding negative 1? We have negative 2 and 0 should give us the same output. Negative 3 and positive 1 should give us the same output. And there's the graph of this particular g in this example. This would be g of x. All right. Ooh, this one, we're taking it up a notch. We have a lot going on here. So first of all, our parent function, well, it's the same as all the others because I see that absolute value. We're going to say f of x is equal to the absolute value of x. And now we have a few things going on. This negative sign indicates that we do have a reflection. So we have a reflection about the x-axis. Reflect over x-axis. Okay, the next thing I like to do is figure out where the vertex is. So figure out these horizontal and vertical shifts. Remember what we're looking for. Inside the absolute value, we have like x minus h and then plus k. So we want to consider what this would be. This tells us how it's moving left or right. This tells us how it's moving up or down. So our horizontal, it says minus 2. That means that we're shifting it to the right 2 units. Right 2 units. And then our vertical transformation. So it's going to be the same as what it looks like. It says minus 5. That indicates it's going to start down 5 units. So what I want to do now is figure out what the vertex is of this absolute value function. So the vertex is going to be located 2 units to the right. That would be positive 2. Down 5 would be negative 5. And then from here, I also notice not only is there a negative in front of the absolute value, there is a 2 there as well. That indicates we have a vertical stretch. A vertical stretch. We'll talk about what that means in just a minute. First, I'm going to graph my vertex. 2, negative 5 is down here. Okay, now this vertical stretch is taking the graph, and normally we would go up 1 over 1, or because it's negative, we would go down 1 over 1. But in this case, we're going to go down 2 over 1. So we're going to go down 2 over 1, down 2 over 1, down 2 more, down 1, 2, 1, 2 over 1, down 2 over 1. Stretches and strengths can be a little bit more complicated. So if you want to create a table of values, definitely do that, because that will help kind of just verify these points, because I know this can be confusing. So when we do our table of values for an absolute value function, it's good to have 5 points where that vertex is in the center. So we want to make sure this is the vertex here. The vertex is 2, negative 5. Okay, so now we want to choose the points that are around 2. Well, to the left of 2 is 1, and to the right of 2 is 3, right? So here's 2 here. I'm going to go over 1 to the left, over 1 to the right. That gives me 1 and 3. I know that plugging in 1 and 3 is going to give me the same output, so I only need to plug in one or the other. If I plug in 1, that would be g of 1. We would have negative 2 times the absolute value of 1 minus 2 minus 5. That would be negative 2 times the absolute value of negative 1 minus 5. The absolute value of negative 1 is 1. So that's negative 2 times 1 minus 5, which is negative 7. Now I know that plugging in 3 is going to give me that same result of 7. So I have 1 negative 7, 1 negative 7, which I have right here, and 3 negative 7, which I have here. Okay, now we're going to go back to 2. We're going to go 2 units to the left. 2 units to the left of 2 is 0. 2 units to the right of 2 is 4. So I know that those two inputs will give me the same output. This time I'll go to the right, so I'll do g of 4. And when I plug in 4, I get negative 2 times the absolute value of 4 minus 2 minus 5. Inside the absolute value, we have 4 minus 2 is 2. And the absolute value of 2 is 2, so we have negative 2 times 2 minus 5. Negative 2 times 2 is negative 4, and negative 4 minus 5 is negative 9. So I know that 4 is going to map to negative 9, and so is 0, right? Which is what I have here, 0, negative 9, and 4, negative 9. Use the straight edge to make this nice pointy V, and we can see our graph of our absolute value function. In our last example, we have g of x is equal to 6 minus the absolute value of x plus 3. So first, we want to identify that parent function. What's that parent function? That's right. F of x is equal to the absolute value of x. Now we want to describe the transformation. So this function is kind of written a little bit out of order. This is not how normal functions are written. If you want to rewrite it, you can. It would be g of x is equal to negative absolute value of x plus 3 plus 6. So now it's kind of in function form looking. We like it like this. Actually, it's called vertex form. We can use this. This is the same thing as what we have here, but it's just in a friendlier format to help us with those transformations. The first thing I see is that negative, so that does indicate to me that we do have a reflection about the x-axis. And the next thing I want to do is identify where the vertex is. So let's see, we have a horizontal shift. Remember how we determine the horizontal shift? That would be x minus h. Eek. And in this case, it can be a little bit confusing when there's a plus sign when it's supposed to be a minus sign. So it might help to think about it as x minus negative 3, right? That's how we would get that plus. So this indicates we're moving 3 units to the left. So I'm going to say left 3 units. And we also have a vertical transformation. Our vertical transformation would be the plus k, and in this case we have plus 6. That means it's going up 6 units. This indicates we do have a change in our vertex, or a shift in our vertex. Our vertex at the parent function would be at 0, 0. Now it's going to be left 3, negative 3, and up 6. There is no stretch or shrink because the coefficient is 1 or negative 1. So we're going to use this. Vertex is negative 3, 6, negative 3, up 6 units up here. And then what we do, this is a negative, so we go down 1, and then to the right 1, down 1 to the left 1. From there, down 1 to the right, down 1 to the left. You can see that V forming, and that's what our absolute value graph would look like. These have been graphing transformed absolute value functions. Thank you for